In the previous video, we defined and introduced measures. This video will cover integration. We start by defining integration for simple characteristic functions, then extend to complex and real value functions. There is one requirement for integration using measure theory, which is that the function you're integrating must be differentiable. This is because integration is always done with respect to a measure mu, and the domain of the measure is a sigma algebra. The value of the integration of the characteristic function is simply the measure of the set. So the function that equals 1 on every rational number and 0 on every irrational number that was defined in the previous video is actually a characteristic function. And the integration of this function with respect to the Lebesgue measure is 0. As we can recall, the Lebesgue measure of the set of all rational numbers is equal to 0. So the integration of this function is 0 as well. Integrations of simple functions, which are linear combinations of characteristic function, is just the sum of the integration over each characteristic function multiplied by the appropriate constants. Let L plus denote the space of all measurable functions that map to the extended non-negative real number system. We define L plus as the set of functions that are non-negative because the next case of functions we're interested in is non-negative functions, and then we'll extend this to real functions. So the value of the integration of a function in L plus is a supremum of the integration of all simple functions less than or equal to f. This definition is well defined since we're using the supremum, but it is difficult to calculate. To calculate the value of this integration, we first find a sequence of increasing simple functions that converges to f, and prove that taking the limit of the integration of the simple function is equal to taking the integration of the function itself. The specific partition that generates an increasing sequence of simple functions, which converges pointwise to f, is shown on the screen right now. And the monotone convergence theorem states that given an increasing sequence of functions in L plus that converges to f pointwise, then the integration of f is equal to the limit of the integration of the sequence. With this theorem and the previous sequence of increasing simple functions, we can calculate the value of integration of a function in L plus. The ability to pass the limit inside the integration is a major advantage of integrating using measure theory. Not only does it provide us with an effective way of calculating the integration of a function in L plus, it also enables us to extend properties to difficult cases. For example, the additivity of the integration is easy to prove when we're dealing with simple functions, but because we can pass the limit inside the integration, we can easily prove it for non-negative cases as well. In the cases where we're unable to pass the limit inside the integration, Fatou's lemma states that the limit of the integration is always greater than the integration of the limit. Most of the time, this will be an equality, but an example of inequality could be the sequence of functions f and x is equal to 1 over n. The left side is equal to 0, and the right side is equal to infinity. Extending integration from non-negative functions to real functions can be made by breaking down the function into its negative and non-negative parts. Both of these are a non-negative function, and we can calculate the integration of both of these functions and calculate the difference between these two integrations to obtain the value of the integration of the original function. Of course, there are certain technical conditions, such as one of them has to be finite, so we do not have subtraction of infinites. In the case where both functions are finite, we say the function f is integrable. Complex integration is extended in a similar manner, and integrable complex functions are functions where both the real and imaginary parts are integrable. We denote the set of all complex integrable functions as L1. We can continue to pass limits inside the integration in L1. The dominated convergence theorem states that given a sequence that converges pointwise to f, we can pass the limit inside the integration if it's bounded absolutely by another function in L1. Note that this sequence does not have to be increasing anymore, it just needs to be bounded. The final section of this video will be dedicated towards different modes of convergence. Sequences can converge in many ways. They can converge pointwise, uniformly, in measure, or in L1. There are other modes of convergence, but these four are the ones that we are most concerned with. We've already been introduced to convergence everywhere and uniform convergence during our experiences in Riemann integration. The two new modes of convergence are convergence in measure and in L1. Convergence in L1 requires integration of the absolute value of the difference between the sequence and f to be infinitely small as n approaches infinity. Convergence in measure requires the measure of the set of x such that fn minus x is not sufficiently small to approach 0 as n goes to infinity. To reinforce our understanding of these different modes of convergence, we turn to several interesting examples. The first and third are cases that converge in measure, pointwise, and uniformly, but does not converge in L1, as integration is always 1. The second example converges to 0 almost everywhere, but does not converge in measure, and it does not converge in L1 as well. Finally, an interesting example is the fourth function, which is a function that converges in L1 and in measure, but does not converge almost everywhere or uniformly. This is because the sequence of functions will continue to loop back indefinitely, but the integration of this function will approach 0 as n approaches infinity. Finally, here are some relationships between the different modes of convergence. Of course, convergence uniformly implies convergence almost everywhere, but convergence in L1 also implies convergence in measure, and most importantly, if a sequence converges to f in L1 or in measure, then we can find a subsequence that converges to f almost everywhere.